What sample rate does suspension data need in motocross? I'm often asked this question, and usually it follows on the back of something like the suspension moves at 9 meters per second, so surely I need a fast sample rate, right? So let's take a look at an example. The distance from the Earth to the Moon is 384,000 kilometers. And if we have an object that moves at 1,000 meters per second, so a lot faster than the 9 meters per second, it will take 106 hours to get from the Earth to the Moon. So this means that we can use a sample rate of 100 hours without losing any data. So if we only measure the speed here and then again at here, 100 hours later, and it shows 1,000 meters per second, that means we haven't lost any data. But what if we change the speed that the object is moving at? So if it starts off here at one speed and slows down and then speeds up again and then slows down, and we only sample it every 100 hours, then we've lost this information about how the object has changed in speed over that time. And this doesn't represent what actually happened. So how do we decide then what sample rate is needed for a measurement? Well, there's a theorem out there called the Nyquist theorem, and if you put this into Google, there's a really nice article here that comes up from National Instruments about sampling. And basically what the Nyquist theorem says is that in order to measure a frequency, you have to sample at twice that frequency in order not to lose any information. So they have three examples here. And the first one, it's sampled at the frequency. So we've sampled point 1, 2, and 3. And then when we output the data that's been sampled, we can see it draws a straight line. So we've lost pretty much all of the information other than the fact that at these 3 points, it was at this position. If we sample at twice the frequency, we can see here we have one sample here, another sample at half a cycle, the third sample at a full cycle, the fourth sample at 1.5 cycles, and so on. And then when we output the sample data, we can see here that we've retained the information so that the position moved up and down like this, but we've lost the resolution. And the third phenomenon then is something called frequency aliasing, where basically if you sample the frequency at less than twice the sample rate, you can produce another frequency. So if we take, for example, here, it's sample at 3/4 of the frequency, you get one sample here, another here, another here, another here, and then when you output that, that creates a different waveform again, and obviously you don't want that because it's not representing what's actually happening. So in this presentation, I'll be using some sample data that we collected from the Motoklik system, which is a suspension data system for motocross, where we measure the front suspension movement, the rear suspension movement, the satellite position, and then we can download it to a phone. And this is some sample data that we recorded from a track in Germany a couple of weeks ago. And in the app, we've selected this section of the track here, which is a corner entry along some braking bumps. So the rider was riding along in here like this, slowing down and then accelerating out of the turn. So the graph underneath then shows the suspension data between this point here and this point here and how it moves. And what we're interested in then is the oscillation of the suspension here in these braking bumps, which is the fastest oscillation that we see on a circuit. So what I've done is I've exported this data as a CSV file and put it into Microsoft Excel and created this graph here. So the data shown here is the exact same as what's shown on the phone. If we take this section of the track and we know that it takes 1.5 seconds to travel from this black line here to this black line here, and do a small calculation where we count the peaks. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and divide that by the time of 1.5 seconds. That means on average we have a frequency here of 7.3 hertz. We can do the same for the rear, which then gives a frequency of 6.7 hertz because there was only 10 peaks. So this means in theory that if we use the Nyquist theorem, we only need a sample rate of 14.6 hertz to retain the information from this graph. However, in the National Instruments article, it recommends up to 5 times the frequency to retain information. So that would be 36.5 hertz. So there we have it. In motocross data for this circuit, in theory, we only need a sample rate of 36.5 hertz to retain the information. So what happens then though from using such a low frequency is why don't we do that? So where does all this confusion come from around sample rates? And the answer is data resolution. So let's take a look at that now also. I was sent this YouTube link by Giuliano in Italy, and he's created some very clever software here where he can set up a camera and then trace the position of a suspension using points embedded on the pixels in the camera. So here he has 3 points embedded, one on the axle, one on the bottom of the fork, and one on the top of the fork. And basically, as he rides over here and plays the video back, the camera is able to pick up the position of the axle here along the blue line, and then he also calculates the speed of the suspension movement along here on the orange line. And you can see here how the speed of the suspension really comes up into a sharp point and then starts to drop off again. So this is all compressing very fast, compressing more slowly, stopped, and then rebounding. And we can see how we've lost the resolution of the data quite simply by kind of comparing the position and the speed data. So when we look at the position data, we can see it's pretty much a nice smooth curve like this. However, the speed data comes up to a sharp point and then drops again. And what we'd expect to see in the natural environment is obviously that it would be a very curved line that would follow the speed trace. So this is where we've lost the resolution. But we haven't lost the information from this because the sample rate here was 240 Hertz. So we know that this is actually how the suspension moved at these times. So what I wanted to do was try and recreate this graph and then compare it with 1000 Hertz and 100 Hertz. In order to do that then, I exported the values here from the YouTube video. So you can see here it's 6.24 meters per second and 147 millimeters at this point. So when you watch the video, it actually shows each point. And then I was able to use that to recreate the graph. And this is the graph here that I created in Excel. So this shows the position data, and then this shows the speed data. And what I did next was to fit a trend line to the position data. In order to do that in Excel, you just right click on the line and then press add trend line, polynomial trend line, and it will spit out a formula like this. And then basically you can use that formula to calculate the position at any point along the x-axis here. Now it didn't fit it exactly. As you can see here, the trend line wasn't able to pick up this very quick change in position, and it kind of skips it a bit, and we see that reflected in the speed data then. So these dark blue lines are the original speed plot of the suspension from Giuliano's video, and then the yellow line is the one that's calculated using the fitted trend line here. So we can see it doesn't follow exactly the speed that the suspension moved at, but it does reach a reasonably high speed of nearly 6 meters per second. But the thing that stands out is the difference in resolution. So we can see here how we can see a nice consistent curve all the way along, whereas in the lower sample data it comes to this sharp peak here. Now, of course, I would have liked to reach up to this speed with the trend line and so on, but I think for the purposes of demonstrating my point, it's okay to continue working like this. So the next thing I wanted to do then was kind of compare the different sample rates of 1000 Hertz, 240 Hertz that it was sampled at, and 100 Hertz. And here we see the result of that. So this line here represents the position data, and this line here represents the speed data. And when we look at the values, we can see these blue points here are at 1000 Hertz, the orange points here are at 240 Hertz, and then the gray points here are at 100 Hertz. And for the position data, we can see that even at the 100 Hertz, the resolution has been lost somewhat, but we can follow the curvature very well from a graphical, image point of view. And then for the speed data, we have here the sampling at 1000 Hertz, we have the sampling at 240 Hertz in the blue points, and then we have the sampling at 100 Hertz in the green points. And here there's a bit more of a difference, so we can see there's a slight time delay in measuring the speed of the suspension. And also then we can see how we've lost that resolution. So obviously if you draw a straight line from here to here to here and down here, it's a lot more peaked and edgy than it is to follow the 1000 Hertz example. So from a resolution and an image point of view, okay, there's a loss there in accuracy of the result, but when we optimize suspension on a track, we very rarely just look at one bump on the circuit and then tune the suspension around that bump. We're looking for a compromise across the entire track. So the question goes away from, okay, what's happening in this specific bump, to how can we analyze all of the data at once? And then what decisions can we make on suspension setup based as a result of that? So if we take a look at this graph here, we've got this waveform, and this is with a low sample rate and this is with a high sample rate, and what stands out is the fact that even with the low sample rate we can still plot the curve, and it outputs a similar waveform as it does with the higher sample rate. So what this means is that when we aggregate the data, when we group it together a little bit, we can retain the information and the accuracy, but not have to have as much data to do that, which means we can use a lower sample rate. And the reason why we can do this is because of something called the normal distribution. So if we were to have a field, and in that field it was full of Christmas trees, so we've got different size Christmas trees, some are very short, some are very tall, and then we were to measure the height of all of these Christmas trees together and divide it by the total number of Christmas trees, we would get the average value. So this value here at this point in the curve, let's say it's 2 meters, would be the average height of a Christmas tree. Then what we can do is use a calculation called a standard deviation on this data set, and we will come up with another value here, and basically it would say that when you when you get the average height and then take away one standard deviation, so let's say it's 0.3 meters is the standard deviation, so between 1.7 meters and 2 meters, 34% of your trees are going to be in this category. And then if we take the max and the min of the trees as well, with these four values, then we can represent this complete data set without looking at one specific tree. So this sounds a little bit abstract, but when we apply it to suspension data, what this means is that rather than looking at one specific bump on the track, we can look at all the bumps on the track and then put them into a graph like this and understand how the suspension is behaving with just these four values. So let's take a quick look at that as an example. And this graph here again is the one that we calculated from our trend line from Giuliano's video. So this is the position data, and then this is the speed data. And what I've done then is I've calculated the average, min, max, and standard deviation for both the position and speed at the different sample rates. So this top table here shows the position data for millimeters. So we can see at 1000 hertz, we have a minimum of 43.8, an average of 148.6 millimeters, a max of 201.1, and a standard deviation of 47.9 millimeters. And then we perform the same calculation at 240 hertz and the same calculation at 100 hertz. And we can see here that there are some differences around the average and the standard deviation between the different sample rates. But how much do these differences actually matter? So you can see here the average went from 148.6 millimeters to 146.2 and so on. And what we can do then is we can perform what's called a correlation. And a correlation basically looks at how similar two data sets are to each other. So when we do this correlation on these three sample rates, so when we correlate the data from 1000 hertz to 240 hertz, it comes up saying that the data is 99.98% similar, and then when we correlate 100 hertz to 1000 hertz, it says that the data is 99.81% similar, and that's because we only have this very low frequency on the track of 6 or 7 hertz or whatever it is from motocross data. So what this means then is that when we look at the data as a whole, even down to 100 hertz, we have a very strong correlation with the higher sample rate. And we can do the same then for the speed that the suspension moved at, and that gives out a correlation result of 99.99999 something percent for 240 hertz, and then 99.96% for 100 hertz. So again, we can use this data as being statistically very similar at the lower sample rate compared even to 1000 hertz. So let's take a look at that data from the track in Germany again. So this is the exported data from the screenshot that I showed you, and the Motoklik system actually does sample at 100 hertz. And you can see here every sample point that was measured by the Motoklik as the rider was going through the braking bumps. So we can see here how the Nyquist theorem was saying to sample at twice the frequency, and National Instruments was saying to sample at 5 times the frequency. So if we count the number of points between one peak to the next, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 points there. and we compare that to the 3 points that were measured in the example from Nyquist here, and we see then that we've got plenty of data points here to retain the information. And what we can do then over here is using our normal distribution. So using this histogram, I have measured all of the speeds of the suspension throughout this part of the circuit, and then it plots out a nice normal distribution curve for us here. And basically what we can do is, if a rider went through the same section of track with a suspension that had a softer setting, we could overlay the two histograms, and then basically with the softer setting we would see that the suspension is spending more time here in the higher speeds and less time here at the lower speeds, and that way then we can compare like for like from the circuit without having to look at one specific bump. We can look at all of the data together. And if you want to see an example from the Motoklik of a really high speed part of the circuit, from a suspension point of view, I mean that the suspension is moving at a high speed, we have this example here again from the Germany track data, where the suspension was moving at a speed of nearly 8 meters per second. So here we can see how the rear suspension compresses and comes to a stop and then rebounds more slowly. And here we can see the trace of the speed of the suspension, and again we can see how we've lost some of that resolution here. It's quite peaky on the top, so obviously the suspension in real life moved in a more curved manner than that and slowed down and sped back up again. But as you can see here, we have 1, 2, 3, 4 data points along this compression, which means that we've retained all of the information, and the reason for that is because the suspension didn't change direction in this short of a time. We really don't see that happening in motocross data. So basically the suspension started to compress, rebounded and compressed again in this short of a time, and we weren't able to pick it up. That's not what happened. The suspension just went from this point here to this point here to this point here to this point here, and that way then we can retain that information about the speed of the suspension through this event. But how often is the suspension actually moving at such a high speed? Well, on our website, motoklik.com, if you click on news, there's an article here called "Are They Worth It? Shock Dynos in Motocross." And in that, we actually went in and looked at how much time the suspension is moving at different speeds. And the total time that the fork spent above 3 meters per second is 0.91% of the time, and the total time that the shock spent above 3 meters per second was even less than that again. So really, from a resolution point of view, you're talking about, less than 1% of the time where the resolution from an image point of view becomes an issue, and you can very well rely on the statistical analysis to compare the full data set with one another. So where does data resolution actually matter then? And it really comes down to very specific test environments. So when you're using a shock dynamometer here, what you want to do is have a lot of resolution so you can fully understand the changes that you're making to piston design or shim stack layout. So this graph here shows force versus displacement, and this is an acceleration of the compression, a deceleration of the compression, an acceleration of the rebound, and a deceleration of the rebound. And you really want to have that resolution here so that you can fully understand what's happening to the suspension throughout the different speeds. So if you had a lower resolution here, then you wouldn't be able to pick it out as clearly as to what the differences are. And that's obviously very, very important when you're working with the data in this very human way of looking at an image and then trying to understand it yourself and making adjustments to the suspension based off of what you see in a graph. The more resolution you have, the better. So this is one of the areas where resolution is really, really important. And we can see that in certain instances then. So this is a video from the KTM Talk suspension group there. It was posted up by Audris, I think, from Lab S7. So this shows the effectiveness of their equipment to move the suspension very quickly. So you can see it there, like you're looking at it and you're thinking, wow, I can barely see that with my eyes. Surely you have to have a high sample rate for that. And yes, that's true for a dynamometer setting. You want to have that resolution there so you can really understand the fluid dynamics of what's happening across the piston here. So if I use this laser pointer, so what you're trying to understand by doing a test like this in a very repeatable process, a very controlled environment with a very high sample rate, is you're trying to understand what's happening with the fluid dynamics as it's being pushed through this shim stack here. And then having that really high resolution helps to fully understand that. So as you make changes to the shim stack, so this is the compression side of the rear shock shaft here, and this is the rebound side. So as you swap out a shim here, you want to really understand what's happening at that as a result of that, or if you change the shape of this port, or you file away some of this area here, or add in some float, or change the area that the floats have. You really want to understand what's happening with that fluid dynamics, so you have a good understanding of the changes you're making and what effect they're having on the force field of the suspension. So this is an area where you do really want to have that high resolution. Another area where you want high resolution is for faster motorsports. So for example, if you're driving this rally car here at 100 miles an hour or 160 kilometers an hour down a very bumpy road, the frequency of the inputs you're getting here on the suspension can be much higher than the frequency you're seeing on a motocross track. And for that reason, then you also want a higher sample rate. And the same can be said here for track bike racing. So as you hit the curbs or something, or hit a small bump on the track, that event happens so quickly, you need to have a faster sample rate to keep up with that frequency. So that's another area where you need a higher frequency. Okay, that brings my presentation to an end here. I hope you've enjoyed it and found it informative. I'm always open to debate on this, so if you can pick any holes in my argument here, I'm more than happy to hear it and work through it, because that means that we can all learn together. So you can put the comments down below. And if you would like some more information, you can visit our website, motoklik.com, or you can email me on info@motoklik.com. So thank you very much for your time today, and look forward to speaking with you again soon.